exactly is this module? Because I just looked in Canvas and I didn't see it.
It is not. I didn't put a link into the modules. I probably should have done that, but I forgot. It is. It is in the. If you go to the first part, the first module inside Canvas, there's a link to text notes. So if you go to text notes, you'll find it.
Okay.
Yeah, so text notes will include all the modules, including all the ones that I have written, the ones that I'm currently writing, and also the one that we are currently, on, topic. There we go. All right, so it looks like everybody is here. I'm just gonna do a quick check because I'm just counting the number of participants. There are six of them, six of us. So we are all here. Um, all right, so an update on the person who hopefully will be taking over, this class for me. Um, so I talked to him, and it's a long turnaround time, between him and I. I don't exactly know why, but it is a little bit long. Um, so the last communication was he just did not realize that time is approaching so quickly. So I'm not really sure whether he'll be ready to teach the class next week or not. So I'm gonna keep teaching until he's ready. I looked at the paycheck arrangement, so it's already using a 4 week split. So so I'm not really sure, what we can do, to adjust the arrangement. But anyway, I'm going to keep teaching this class until he is up to speed and ready to teach the class. Alrighty. So this is where we left off last time. Okay, so this was the last sentence that um, we were mentioning in the previous class. So basically, the virtual space is gigantic. Okay, the virtual space has 16 exabytes, and the physical space, on the other hand, is pretty small. Okay, now it is not small by the PC standard. So if you look at a PC, the PC has typically 32 to 64 gigs, of RAM, and that's considered pretty good already. And the IBM mainframe has 40 terabytes of RAM. But 40 terabytes of RAM compared to 16 exabyte of the address space, of the logical address space, is 1/400th of that amount. So so we have a little bit of a disconnect here, right? Okay, we have a lot of the virtual address space is huge, and then the physical amount of memory is actually not that much compared to the logical address space. So that discrepancy is there for a reason. Okay, I'm not really sure whether I wrote about it or not, but the discrepancy has to do with when we upgrade an architecture, we usually double the width of registers. I think it was in the later part of this module, but I can bring it up right now, because I think in this context it kind of makes sense to talk about why we have this, strange arrangement where the logical space is gigantic, of which we really can only use a very tiny portion of it. So the issue has to do with when we upgrade an architecture, we double the size of what we call the registers. So registers are general devices inside the processor. They are in some way a way to store information, but it's not really for too long. So we don't really use registers to store code, for instance. But registers can be used to specify where in memory we want to access, where we want to read bytes. Okay, especially in the data space, where we put all the data. And those registers, so it goes from 8-bit to 16-bit wide, and then from 16-bit to 32-bit wide, and it goes from 32-bit to 64-bit wide. So that was the last jump, okay, for most architectures, including personal computers, including your desktop and your laptop computer. That was the last jump from 32-bit to 64-bit. So when you look at the width of the register, it just doubled, okay, which is kind of no big deal because according to Moore's law, the transistor density inside any type of electronics is going to double every 18 months. So we are kind of right on schedule there. However, but when you look at how much space it can address, it is 2 to the power of 32 before, which is adds up to 4 gigabytes, and it is now 2 to the power of 64, which is 16 exabytes. That is why we have this gigantic jump in from when we went from 32-bit to 64-bit. The amount of locations we can specify in an address space just jumped by a whole lot. It basically jumped by it jumped by 4 billion times. So that is the reason why we have this kind of discrepancy when it comes to how much potential addresses do we have in the address space versus the size of a register. All right, so do we have any questions about that discussion? If you don't want to think about binary numbers, think about base 10 numbers. So if you think about base 10 numbers, we went from 4-digit to 8 digits. So when you look at the width or the length of a number, 4-digit versus 8-digit, yeah, they only it just doubled. But when you think about the quantity that a 4-digit number can specify in base 10 versus a 8-digit number in base 10, that is a big big jump, and that's basically what we are seeing when every time we double the size or the width of a register inside the computer, we basically increase the address space by a huge amount because it is an exponential type of relationship. So now we're moving on to section 2.2.3, and this is a really long one. This is basically the very last the very last subsection, but it breaks into sub sections. And I'm not sure whether you guys can do this or not. If you go to add-on, I can do this because I'm authoring the document, but I can go to a table of contents and I can show it on the sidebar, which sometimes is kind of handy because it gives me a map of where I am at this point and what are the subtopics that I have to go over at this point. Can you guys see that, or can you open it up on your side?
I don't know.
Okay. All right. So it is under add-on. If you open the document, it is under add-ons, and then it's under table of contents. You may not be able to do it because you are not the author or editor of the document. I can also
see it on yours though, but I can't. I haven't tried mine.
Okay. Yeah, I can insert the table of contents at the very beginning of the document too, if that is useful. So I can do that too. All right. So now we kind of dig into some of the more, I would say, advanced topics, in the topic of how a computer operates. So there are many reasons why we have a map from virtual memory to physical memory. Virtual memory is basically determined by the width of the registers. Okay, so when we have a 64-bit register, then we have 16 exabyte of virtual or logical memory space. On the other hand, physical memory is mostly determined by practical concerns. How much RAM can we actually install on a computer? Now, you might say, well, if we can install 40 terabytes of RAM, sure, I mean, we can just spend more money and buy more DIMMs and then put everything into, just add more components into the CPC drawer. Well, that turns out to be not possible because the distance between the components inside a CPC drawer is actually significant. It is actually important. We can only allow the CP, the central processor, to be a certain distance away from the DIMMs. Okay, if it goes beyond that distance, then we have problems. Now, I'm not going to explain the physics of the problems, but for those of you who are curious, it has to do with the capacitance and also inductance of a conductor. So we cannot place components too far away, which also means you can't just kind of go like, okay, I will include I will hook up 20 DIMMs to one single CPC drawer. It's just physically not possible. Okay, so there are a lot of limitations why we have a limited amount of physical memory. It's not just money. A lot of this has to do with physics as well. All right, so the explanation here is availability, why we do mapping from virtual memory to physical memory. So, and this is something that we just talked about. Basically, the amount of addresses you can use in virtual/logical memory is 400 times of what you can physically fit into a mainframe. So as a result, mapping makes sense because now you can basically say certain locations do not exist, and we can just focus on the locations where we really want to have actual memory content corresponding to those particular addresses in physical space. This part here explains what this is the whole discussion about why we went from 32-bit all the way to 64-bit and not just jump by a little bit. Okay, because you might think we can just increase the width of an address not by another 32-bit. We can just extend it by 8 bits so that it becomes a 40-bit address. In which case, a 40-bit address would be basically 1 terabyte. So that's kind of reasonable, right? 1 terabyte is kind of reasonable by today's standard. And even 48-bit, is not too bad because 48-bit is 256 terabytes, and the physical RAM we can install in the system is 40 terabytes. So it's not off by too much. So this has to do with whenever we change an architecture, we like doubling. Okay, so computer architecture people like to double the sizes of registers, and that's why you don't usually see a 32-bit extending to 40-bit and then 40-bit extending to 48-bit, because every single time we extend, we want to double it. So so this part just kind of explains the math stuff that we just talked about. So I'm not going to get into this paragraph too much because we just kind of talked about it. So in reality, when I talk about jobs, we're talking about computer, mainframe jobs, not like your job. So many computer mainframe jobs, especially the legacy jobs, only require a small amount of memory. Now, I don't have any statistics of what is the percentile of jobs that require up to this much RAM or this much memory. But if COBOL programs are still being used, and then last time I served in an IBM, there's a name for those. It's not a workshop, but it's basically a chance for people to kind of work together on the document. But last time I talked to several people from various state agencies. They were using tools from the 80s. Okay. As a result, in the 80s, those IBM mainframe computers, they don't even have the resources to, they don't have the amount of RAM that we talk about these days. So those programs cannot possibly be using a lot of memory. So all of these programs will only use a very small amount out of this many addresses in the logical address space. So we are talking about, out of 16 exabytes, we might be using 2 gigabytes. That's a lot already. Okay, I suspect most jobs would fit into maybe hundreds of megabytes, if not less. So we are talking about a very tiny amount of memory that is actually needed to run our jobs, compared to a gigantic amount of addresses that the hardware can allows us to address. So let me think about how we should put this. Okay, think about the Pacific Ocean. Okay, so think about the Pacific Ocean being your logical address space, the virtual address space, and think about ships. On the Pacific Ocean, those are the actual locations in use. That's I'm not really sure about whether the ratio matches what we are talking about here, but I think that that's a visual thing that you can do, right? You just look at the ocean. That is how much. That's the address space. That's the logical address space. But of the entire logical address space, very few locations are actually being used, and those will be represented by ships, that are floating on the Pacific Ocean. So
That's a good analogy.
it really is kind of it's really is that kind of ratio, if you think about it. So most of the locations are not really they're not really used. So what do? Well, we just basically go, okay, we'll use a very small amount of the available locations. And so that's one reason why we have memory mapping, because we just look at this gigantic space and go like, okay, we are using a little bit here, we're using a little bit here, we're using a little bit here, but in between there's a huge amount, right? There's a huge distance between ships on the Pacific Ocean. So it's a waste if we just go like, okay, we're gonna use actual memory locations for that empty space. That's just a waste of space. So instead of doing that, we basically go like, okay, uh, we'll map the surface, okay, on the deck of this ship to this little area over here, and then the next ship is going to map to another area that is adjacent. So in a way, we are creating a mapping mechanism, and so that we are combining the deck area of all the ships into one small contiguous piece of land. So
Okay.
So that's kind of what we are doing. We're combining the surface areas of all the decks of all the ships, in the ocean, and we're just going like, okay, we are combining all of that into a small area that is actually land. So when you are on a ship, on the deck of a ship, you're actually not on a ship. You're actually standing on land, except that land is through a portal, accessible in the middle of an ocean. Sort of like that. I'm not sure whether this analogy is making things more confusing or not. And over here we have a binder example. So you basically end up with magical pages. Most pages don't really exist, and then some magical pages are basically portals, and they will basically map that magical page to an actual physical piece of paper that is somewhere else. So that's kind of what is going on with memory mapping. So that's so we are talking about. Oops. Okay. I just dragged the wrong item. There we go. Now we're back here. All right. So we are talking about this paragraph here, as an analogy of pieces of paper in a binder. So the next paragraph here talks about, so how should we do this translation? How should we do this mapping? Are we mapping bytes individually? Well, that is not impossible, but it would be very, very expensive, because every time you map something, we need some kind of hardware, electronics, that involves transistors, to help us to do this translation. So if we map only, if we map byte by byte, then we're going to end up with a lot of transistors, just to do this translation, which is unnecessary, because a lot of times you don't really need to say there's a byte over here, there's a byte over here, there's a byte over here, there's a byte over here. Most of the time, if you think about, okay, think about the deck area of a ship. Okay, if we limit the granularity of mapping, to a single square foot, then you go like, But that's just not very reasonable because what kind of a ship only has 1 square foot of deck area? There's no such thing, right? Most ships, probably have, I'm just guessing, if it's, ocean worthy, we're probably talking about 100 square feet to say the least, right? Maybe 1,000. So it makes more sense to basically go like, okay, when we're doing this kind of mapping, of the deck on the ship to actual land, we'll do it by chunks, okay? And then each chunk is, I'm just thinking about the width of a ship on the Pacific Ocean. We'll just do it by 10 by 10, okay? We'll say it's 10 by 10 feet. So we have a square that is 10 by 10. That is the minimum amount. That's the granularity that we can do when we are mapping deck area on the ship to actual land in this kind of magical setting. Does that make sense? I mean, I just want to convey why we are not doing a square foot type of mapping. We're doing a 10 foot by 10 foot area type of mapping.
That's because you have so much space. You don't want to waste it, so you want to use it in bigger areas.
Right, because if you do it every square foot has 1 map, then you need to use a lot of resources to remember which square foot maps to which square foot.
Okay.
But if you do it with 10 by 10, then you're reducing the amount of mapping by 100 times, because instead of every single square foot has its own translation map, now you just say, okay, we have a larger area. Every square 10 by 10 has 1 translation mechanism. So now we are reducing the amount of translation mechanism that we need by a whole lot. In the case of virtual memory on an IBM mainframe computer, we have we basically have blocks of 4,096 bytes. So that's the amount that we are talking about. So every time we do a mapping, when we talk about memory mapping, we are mapping a chunk or block of 4,096 bytes at a time. And that part is discussed. I think it's down here, down below somewhere else. But there's another reason why we want to do memory mapping. So the other reason to do memory mapping has to do with these 2 paragraphs. So I'm going to quickly explain what these 2 paragraphs are explaining. So if you imagine you're in a high school setting and you're teaching history, and you have textbooks that you need to distribute to the students. So we're going to make an assumption that each textbook has 512 pages. Of the 512 pages, the majority, like 384 of those pages, are instructions. Okay, so they're basically just text, diagrams, pictures, and so on. And only 128 pages are exercise areas where the students can fill in the blanks. They can, they have multiple choice questions, or it's an area that the students can jot down their notes. Okay. So now the question is, what is the best way to distribute the textbooks? So if you make 32 complete copies, each one having 512 pages, then you will end up using 16,384 pages, because that is 32 times 512. So are we doing okay with this math here?
Yes.
Okay. So this is what we need. This is the only thing we can do in reality. Okay, because in reality, well, student A and student B cannot share a page. So now we think about special pages on the textbook. Okay, we will talk about special portal pages on the textbook. So those pages are not real. They're basically just a portal to a page that is sitting somewhere else, okay, like in the library or in the classroom, or something like that, okay. So it's basically just a portal. When the student look at a page that is actually a portal, the student is actually looking through the portal onto a page that is somewhere else. So when we have this type of if we have this type of technology, then we can say 384 of the pages in a textbook, they can be portal pages, because because all 32 students can share the same instruction page. If it is really just text or diagrams or pictures or something like that, they can all share the same one. There's no need to make one copy of a page for every student out of the entire class of 32 students. So if we can magically, share those pages where students don't need to jot down their notes or to answer the questions and whatnot, then the total number of pages that we actually need. Now, when we talk about these pages, they are actually sheets of paper. So in this case, we have 384 shared pages because we can use the portal technology, and then we only have 32 times 128 of the pages corresponding to the pages where students can actually write something. So the total amount of pages or sheets of paper that we need is only 4,480 instead of the original 16,384. So are we doing okay with this analogy?
Yes.
All right.
Yes.
All right, excellent. Because I was a little worried that sometimes my analogy is too sci-fi based, and people who do not watch a whole lot of sci-fi may not have a frame of reference to understand the concepts. So I'm glad it
something that just comes to my mind that you could use in this example would be that the 300, what is it, the 300 and something pages, 384 pages could be on a computer so that everybody could view them instead of having to print them, instead of a portal.
Oh, okay, sure.
Kinda.
Yeah, it kinda. Okay, so the difference between the two analogy is I still want to have the pretense that each student has a binder that has 512 pages in it.
Okay, I got it.
Yeah, so that's the thing, because it has to look the same to each student, and there's no distinction between pages that include text only versus pages that has exercises and fill in the blanks, type of activities.
Okay.
To the student, there should be no distinction. So that is the thing, right? Okay.
Okay.
Yeah, because the student is basically the tasks running in the address spaces, so they don't know. I mean, they have no idea which page is real, like physical, this is actually made out of tree product, and which page is virtual. Okay, this is just a portal. That page is not actually in your binder. The student cannot tell. The program or the task that is running in an address space cannot tell. A location is a location. It has no idea whether it is real or not.
Okay, that makes more sense now.
Okay, great. So that's good. So this cannot be done in real world, okay? Because otherwise, we'll be doing that, okay? Instead of having my kids to carry around, backpacks that are half of their own weight, okay? They'll be carrying much lighter backpacks. So it doesn't happen in real world. However, in the computer, mainframe or otherwise, okay, your PC actually does about the same thing. Memory mapping allows certain pages in virtual space to be mapped to the same physical memory frame. So this is referring to the specific terms that we use in IBM documentations. So when we talk about a chunk of bytes, 4096 to be exact, in virtual/logical space, it is called a page. So a page is 4096 bytes in a contiguous space in logical/memory address space. when we talk about the same amount of locations, 4096 bytes, as a contiguous area in physical memory, that will be something that will be a resource in the DIMMs that you install or you can see inside the CPC drawer. That is called a frame. Okay, so page is virtual, frame is real. So if there are 20 concurrent jobs of compiling different COBOL programs, then the pages corresponding to the compiler code can be shared. What cannot be shared would be the program that is the COBOL program that is being compiled cannot be shared, because these 20 instances of running a COBOL compiler, they are likely to be compiling different COBOL programs. But the compiler itself only needs to exist in physical RAM with only one copy. So that is a scenario where we can save a lot of space in terms of physical memory when we have concurrent jobs that just go like, okay, we are all doing about the same thing, or we need about the same kind of code, so we only need one copy of those things. So are we doing okay up to this point? This is the second rationale of why we would like to have memory mapping.
Yeah, that scenario made sense.
Okay.
Thank you.
And I think Lupe had a question back there. Nope. Okay. All right. So there is another reason over here. This is for communication. Now this one is kind of interesting. So in order for two tasks, to communicate, two tasks that are in different address spaces to talk to each other, it depends on the operating system. So in the case of Unix or Linux, or to a large extent Windows, the way they communicate, these are, we call it inter-process communication. They are typically done using some kind of serial communication, like a socket. Okay, it is very clean. It's a very clean interface, but it's also very inefficient. And the next paragraph talks about why this approach is not efficient. This approach is also called a file orientation. It's basically using the concept of a file in order for one process to share data with another process. But it is inefficient because the process that is producing the data that needs to be shared need to first convert the data into a serial format. Then the serialized content is then transmitted either as a socket, as content of a socket, or it is actually stored into a file, or it is fed into a pipe. But in all of these cases, okay, the receiving end now needs to look at the serialized version of the data and then reconstruct the original item. So that's a lot of overhead. And that is usually the approach used by Unix/Linux type of application programs. File orientation, basically is file-oriented data sharing is also inefficient. I explain here why it is inefficient, because everything has to be serialized. But there's also an extra overhead, because if you're using a socket, then TCP/IP needs to be basically you're coding everything into a stream using TCP/IP, and then on the other side, you have to decode a stream and then get back to the original serialized data. Then you have to reconstruct it into the data structure in memory. So that's a lot of different steps. Now, the nice thing about this approach is it is very clean, and it's also very scalable, because these two processes that are talking to each other using a socket, they can be on the same installation. In other words, they're just different processes running on the same computer. They can also be running across a small local area network. They can also be across the entire internet. It doesn't make any difference, because once you get down to, once you're using TCP/IP, it takes care of all the routing. It takes care of all the error checking, retransmission, and whatnot. So it's a very clean interface. It's a very clean and scalable interface. So that would be the approach used by Unix/Linux type of applications. Now ZOS is interesting that it takes an entire different route. So instead of doing, instead of having a clean interface of, okay, everything is a file, it's using the approach of, why don't we just share a certain memory area between the processes, and now they can talk in a very, very efficient way. So to understand this part, okay, you can kind of, I'm trying to think of an example, where this would be, this would make sense. Because I have to think about something that is spatial, and then you have to translate it into something that is non-spatial, something that's serial, and then on the other side you have to reconstruct it as something that is spatial. Whew. I have some examples in my mind, but I have to pick one that doesn't need a that doesn't need specialized knowledge to understand. So let me try to think of one. Okay, pictures. Okay, so we'll just talk about diagrams. Okay, so in the classroom setting. Okay, so let's just say that one student wants to, during class, doing what the student is not supposed to do, is wanting to chat with another student, using the history textbook, no less. So so the Unix approach is to have the student to be able to call the other student and only be able to use words, okay, to communicate the concept. So if one student is thinking about a funny picture, okay, then the student will have to describe the picture, right? Okay, in my mind, or I have this visualization of a very funny image of blah 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 blah. So now the student has to use words serially, describe the mental picture that the student has, to the other student. So the fact that of using the phone, using the phone but voice only, so we are not texting pictures and stuff like that, is serial. Okay, so the other student will not have to listen to the first student. The recipient has to listen to the transmitter and reconstruct that mental image to understand what the first person is saying. That is not efficient. Okay, it takes a lot of time to do that. So the opposite, or the other approach, okay, the IBM approach, is to have the two students. Remember that history textbook binder thing? Well, guess what? There's a certain area where the students can go like, okay, this is not shared with the entire class. I just want to share this with the other student over there. So now we have, these magical pages that map to an actual piece of paper, a sheet of paper, but the sharing is not done with the entire class. It is only done with another student. So now, when one student starts to doodle something funny, the other student gets to see that picture like right away, because they are actually looking at exactly the same physical page. Is that okay? I mean, is that working with you guys?
Yes.
Okay.
Yeah, that works.
So instead of having a global scope of sharing, this is now a localized scope of sharing. I'm only sharing with my buddies, not the entire class. And whatever I draw on those magical pages, all of my buddies will see in real time at exactly the same time. So there's no lag, no latency whatsoever, because they are actually seeing the content. We are actually looking at the same physical piece of paper because of the portal and also because how I set up those portals to be shared, to share one single sheet of paper. So that turns out to be the approach that IBM took when they need to think about, okay, how do we want the different tasks to share data? So instead of using sockets and files, IBM says, why don't we just share a region of memory so that different tasks can talk to each other? So this method is extremely efficient, okay? When it comes to having two tasks running on the same CPC drawer. Now I have to point out, CPC drawer because the 5 DIMMs that we installed, into a single CPC drawer, that is local to the CP of the same drawer. And with the Z15, I think that's the current latest and greatest IBM mainframe. The current one, one CPC drawer can have 4 CPs, and then the 4 CPs, basically are sharing the same 5 DIMMs, in the same CPC drawer. And that, if all the tasks, that need to share, using this mechanism, if they're all living on the same CPC drawer, that sharing is really efficient. Okay, so there's basically no overhead involved in this type of sharing. So now the next question is, but tech, the IBM mainframe can look at the entire setup, up to 5 CPC drawers, as one single installation. An LPAR can potentially span across multiple CPC drawers. What about that? Well, as it turns out, if that is the case, each CPC drawer has a SC chip, and that particular SC chip can create the illusion that the memory are all connected, across the CPC drawers. So even though physically they are not, but the SC component, the system controller component of each CPC drawer, can facilitate very, very high-speed communication between the CPC drawers, so that it can still be seen as one single memory space, physical memory space. So the sharing of these pages can still be done even if these tasks are not running in the same CPC drawer. And in the same and this method of sharing memory can be done even across frames, across installations, because as long as they're inside the same sysplex cluster, the CP, it's CP's CF, sorry, the CF coupling facility, which is a hardware component, actually does allow a illusion of shared memory across tasks that are running in different installations in the same sysplex cluster. So that's really that really is a big differentiating factor between IBM mainframes compared to Unix and Linux, because this approach is entirely different compared to the other operating system. So are we kind of still doing okay with this discussion?
Yes.
Yes.
Okay. All right. So I know some of you are taking classes about Unix. Is that right, or is that done already?
It starts in June.
Hmm.
The first week of June.
Okay. I thought somebody told me last week that they just came home from a training with using Unix. I could be mistaken.
We were doing Rex, and then our next one's going to be Unix.
Oh, okay. I see. Okay.
Yeah.
Yep. All right. So the complex memory space segmentation has to do with backward compatibility, but physical memory can use efficient protection of address spaces from each other, as well as efficiency of data sharing. So the complex address space segmentation of ZOS has to do with these factors: backward compatibility, and that's why somebody from the previous class asked about the above the bar and below the bar. That turns out to be the bar because of the System 370 central processor limitation. The space segmentation can also allow us to use physical memory more efficiently. It will help us protect memory address spaces from each other. So this part has to do with the 32 students in class. They actually have 32 different binders. So except for the special pages where we say, okay, this is a portal page, you're actually looking through a portal to some other actual physical sheet of papers sitting somewhere else, you can actually have real physical sheets of paper in those binders. So those would correspond to space, the space where you want students to jot down some answers, fill in the blanks type of questions and whatnot. So with those, each student actually has the student's own copy. So if Timmy is naughty and starts to doodle and and draw certain things on those pages, guess what? Nobody else is going to see it. Okay, only Timmy get to see it, because that is a page, a physical sheet of paper that is only in Timmy's binder, and the other 31 students don't get to see it. So if Timmy gets really frustrated and start to tear out pages from the binder, doesn't affect anybody else. Okay, so that is the protection of address spaces, so that tasks cannot step on each other, not easily. Okay, and then the last portion has to do with data sharing. We just talked about that, of how certain pages are actually shared between two different address spaces, so that the corresponding tasks can use the shared memory portion to communicate with each other in a very, very efficient way. All right. So this entire section, 2.2.3.1, is really just trying to explain the rationale behind memory mapping. Section 2.2.3.2 talks about paging, which is a different mechanism. It still has to do with virtual memory versus physical memory, but it is a different mechanism. So paging has to do with the fact that not every single how should I put it? Not every single page of memory needs to be in physical memory. So let's think about an example. Okay, let me see if I think I had an example down here, or maybe not. Okay, so I got this example here. So we are still in the history class. We have 32 students, and then each history textbook has 512 pages, of which 128 correspond to exercise areas where we really need one sheet of paper per page per student. So there's nothing we can do about saving those pages in this class. Okay, so let me pull up a calculator so that we can actually look at some of the calculations. So give me a second here. Oops, BC. There we go. So this is a very crude type of calculator. Okay, so just focus at the bottom of this command line interface. All right, so we have 32 students, and every student has 128 pages. So that adds up to 4,096 pages of paper that correspond to actually sheets of paper that we need to install into the history textbooks. All right, so let's just say the school is very poor, and at any time they can only afford to have 2,048 actual sheets of paper. Okay, so now I just throw out this number so that we can visualize it. Okay, so 4,096 are needed because we have 32 students and every student needs 128 sheets of paper in the binder, because those are private to each student. But the school is poor. They can only afford to have 2,048 sheets of paper at any time. So now we have a little bit of a problem, don't we? Yep.
What about printing back to back?
Well, there's another solution. It's called recycling. So what we're going to do is we are going to basically keep track of which chapter we are on. So the chapters that we are not on yet, guess what? We are not going to print those out. Those pages, they're sitting somewhere else, but we don't need it yet. So we are not. So the district or the school can basically defer to the district or some other resources and go like, okay, I don't need these these content yet, so I'm just going to archive those things somewhere else. So when we move on from one chapter to another chapter to another chapter, some of the past chapters, okay, some of the pages of the students' exercise or the students' answers, they don't need to be in the textbook in the binder anymore, because that's something that we talked about like 3 months ago. We don't need it back anymore, or not anytime soon. So those would be archived. Okay, think about microfiche. Okay, for those of you who are still remember what is a microfiche, is that okay? I mean, because I want to make sure the reference is okay with everybody.
Yes, I remember microfiche.
I know microfiche.
So we're gonna use microfiche and say, okay, we don't need the answers to these questions from 3 months ago. So we'll use microfiche, take pictures, and then send the microfiche away to be stored. And then what we'll do is we're gonna erase those pages, okay, the actual sheets of paper that correspond to answers from questions 3 months ago. We're going to recycle those pages. Okay, so we're going to recycle those pages, print new content on it for the current chapter, maybe even the next chapter or so. So using this method, now we can just use 2,048 actual sheets of paper so that students have some place to write down their answers. All right? So this is the trick, okay? So this is the trick, is when we run out of paper, we just look at the existing sheets of paper and go like, this one we haven't touched for a long time, so let's not lose it. Okay, let's use microfiche, back it up, send it away, then I can reuse that piece of paper for something that I need right now. Are we doing okay so far with this analogy?
Yes.
Okay. So let's just say that one day, Timmy, said, I'm not getting a very good grade. How come, my grade is just a C at this point? So Timmy, said, okay, I need to go back and look at, how I answered the questions, from 4 months ago now. So what are we gonna do? Well, we just call up district and go like, okay, can you send over the microfiche corresponding to Timmy's answer to these questions 4 months ago? So the district sends back the microfiche, but Timmy cannot read microfiche. Okay, Timmy can only read things on physical sheets of paper. So the school is now taking the microfiche and print the content of the microfiche using one of the existing pieces of paper, so that Timmy can look at that page and go like, oh darn it, I knew I was wrong answering those questions, and this was how I got those wrong. So are we doing okay so far with this? Because it's not just for backing up some pages, but we can always recall and go like, I need to refer to one of those pages that's archived. And when you do that, you basically have to use one of the current sheets of paper and erase it so that you can print the content of that microfiche onto that piece of paper. So
makes sense to me.
All right. So using only 2,048 actual sheets of paper and using the microfiche mechanism, which is, well, in this particular story, it's more cost effective. Now we can have the pretense of actually having 4096 actual pieces of paper, but in reality we only have 2048.
Is this what they refer to as swapping?
Yep. No, this is paging. Paging? Yep, this is paging. I'll talk about swapping in just a little bit. This is paging. So paging is a mechanism where one page in virtual space can be written to an auxiliary storage, and once you have a page, the 4096 bytes, okay, so getting back to the notes here, so when you move 4096 bytes from physical memory to auxiliary storage, the content, the 4096 bytes on the auxiliary storage, is no longer called a frame, it is now called a slot. So there are three terms, okay? Each term is referring to a block of 4096 bytes. If it is living in virtual memory, it is called a page. If it's living in physical memory, it is called a frame. No, did I just say frame earlier?
Yes.
Okay, let me.
You said virtual's a page, physical memory is
frame, and then if it is paged out to auxiliary storage, it is called a slot. And somewhere in here, I actually make those references. So we got page, frame, and slot. So using this mechanism, okay, in theory, if we use this mechanism, we can reduce memory requirement to a very, very small amount. So let's go back to the school example. Okay, so we can go back to the school example, and so we say, well, we know that students do not need to refer to more than 2 pages at a time. So now we say, maybe we can reduce the number of actual pieces of paper to only 64. So every student only gets 2 actual physical pieces of paper at any time. Well, that may be doable, but now we have to do a lot of traffic with the district, with all the microfiche, because a student wanting to refer to an exercise, that is beyond the 2 pages of content is very high. So every single time the student goes like, I want to refer back to something that I learned last week. Oops, that thing is already microfiche and archived. Now you need to ask district and go like, okay, can you send me that microfiche so that we can print the content of that microfiche on a piece of paper? But when we do that, we have to back up that piece of paper first onto microfiche so that we don't lose the content of that piece of paper before we reuse it for something that is already stored on microfiche. So now we have a lot of printing from microfiche and then recording on microfiche and a lot of traffic back to the district office. This is analogous to actually doing work with I/O devices. Every single time you want to page out and store something onto auxiliary storage, it takes a huge amount of time. It is very expensive from the perspective of taking up time. So that's why we don't want to reduce the amount of physical memory to a very, very small amount, even though it is in theory possible, but in reality, that can basically render your mainframe useless. So there's a little bit of math that I worked out here. Okay, so in theory, the mechanism can reduce the physical memory capacity to a very small amount, okay, because you can say, well, we can always swap it out to the disk. When we need it back, we'll swap it back in. So, things are good. Okay, I should say page because swapping refers to a slightly different mechanism. So this is paging, okay? So paging can page out and page in, 4096 byte, at a time. Okay, that's paging. Now, paging has a performance price tag, and potentially it can be it's a very high price tag. So what I have worked out here is based on DDR4 memory, and I'm pretty sure IBM uses something that's faster, but not like a whole order of magnitude faster. So in terms of order of magnitude, we're still fine. Okay, so not a problem in terms of order of magnitude. So we'll just kind of focus on this number here. So this number is saying that using just physical memory, we can achieve a data rate of, okay, I shouldn't say transfer rate, I should say data rate. There's a slight difference between the two. Data rate is measured in bytes, and then transfer rate is measured in number of transfers per second. So I worked out, with 5 DIMMs, each one installed with DDR RAM that is capable of 2.666 gigahertz. We can basically end up with this type of transfer rate. So this transfer rate is telling you that we can transfer 85 billion bytes per second. That's basically what it is saying. 85 billion bytes per second when we are accessing just memory. So now we look at the auxiliary device, how long, or how much time it takes to write content to a device, to an input-output device. PCIe is Peripheral Component Interconnect Express, and the highest standard today is version 5.0, and it can have 1, 2, 4, 8, or 16 lanes, and 16 lane is kind of the maximum. So this is maxed out. Okay, we're talking about top of the end PCIe controller. That is capable of 63 gigabyte per second. So when you compare these two numbers, well, they don't seem too different, right? I mean, they're at least in the same order of magnitude. 85 versus 63 doesn't sound too bad. Okay. Well, unfortunately, this is basically the ideal case where your input-output device can actually keep up with the PCIe bus speed. And that does not happen. So some people may say, but we can use solid-state drives instead of regular hard drives. So there's no seeking, there's no waiting for the rotation, of the sector under the disk head, and there are no physical latency involved. Well, even without those physical latency, there's still a latency, or basically it's also a turnaround time. So the turnaround time, basically referring to asking the I/O device to store something to the time that the I/O device is actually done doing it, is about 0.1 of a millisecond. Now you might say 0.1 of a millisecond is a very short amount of time. Well, that it is. Okay, 0.1 millisecond is a very, very short amount of time. Assuming you need that much time, to access a 4K sector. 4K is 4096, so this is basically corresponding to a slot because it is being stored on an auxiliary device. During that time, if you were using RAM, we could have transferred 8.53 megabytes of RAM content. So the amount of time to transfer 4096 bytes to or from an auxiliary device, if you were using RAM, that same amount of time could have transferred 8.53 megabytes of RAM. All right, so what kind of order of magnitude are we talking about? We are comparing 4,000 to about 8 million something. So if you just do some rough rounding, we are talking about a 2,000-fold change, or 2,000-fold difference in terms of how fast we can transfer data. The I/O device is basically 2,000 times slower compared to RAM. Are we understanding the order of magnitude here? Why paging, the act of storing a physical RAM frame onto a I/O device slot, or vice versa, the other way around, is a very expensive operation. Are we getting that part?
Yes.
All right. So if paging is done occasionally, it's not bad. Okay, there's a very little impact to the overall system performance, because well, even if you don't have paging, even if your program is always resident in physical RAM and there's no paging at all, well, guess what? Sometimes your program will still be stalled because it's asking the database to do something, and then the database itself has to access the hard drive or some kind of auxiliary device. So even if you are not paging, a program typically still has to do some degree of input-output, using the auxiliary device. So the minor paging is not going to change the overall performance all that much. But if you push this to the extreme, in other words, you want to save the school a whole lot of money and only give each student 2 pages of physical paper, then we have a little bit of a problem. Because every single time the student wants to do something, it's like, oh, the page that I have is not the page that I want. Now you have to call up the district again to get the microfiche. You first have to record what the student has on that page, into microfiche. Then you have to get the microfiche of the page that the student wants to read, and then print it on the page on that piece of paper so that the student can read that page. So that can be very bad. Okay, so if you push this all the way, it becomes, this is a term called thrashing. So thrashing happens when you have so much paging activity going on that the input-output channels are basically saturated. And when I use the term saturated, when I say the input-output channel is saturated, it means there's no capacity left. Okay, it is being used 100% of the time just to page things in and out. So when that happens, okay, on a PC, okay, what you will end up seeing, I'm not sure whether you guys remember those PC desktop computers that had LEDs corresponding to disk activities. Yes, I'm dating myself here. That's basically corresponding to a system where that LED stays lit the entire time. Your hard drive is just thrashing because it's paging in and paging out, and the program or your computer, your entire system, seems to have crashed. But it really has not crashed. It's just that it's very, very slow in terms of your performing operations. Did anyone have that experience, when you used a computer that just doesn't have enough memory to handle everything that you want to throw at it?
Yes.
Okay. And what is the solution to that problem? When you have a computer that is kind of slightly too old, and then it doesn't have enough memory, and then causing this type of issue, so what typically do you do to fix that problem?
Have to wait.
You have to clean it out or upgrade it, I guess.
Okay, I like that idea. So what do you upgrade? Do you get a larger hard drive? Would that address this problem?
No.
What would? What kind of upgrade will fix this problem? How about getting a
Memory.
faster? Sorry?
Memory.
Memory, exactly. So adding memory would fix an issue. If you have a system where it is very slow because of thrashing, getting a faster processor is not going to help, because the processor is basically twiddling its thumbs all the time, waiting for things to page in and page out. Think about the student, okay? Think about the student that really only has 2 physical pages. Every single time the student says, I need to go back to the quiz from last week. Well, we need to send a request to the district. Okay, we need to microfiche your current page, and then when the microfiche comes from the district, we have to print it on a piece of paper, then you can read it. So for the most part, the student is just twiddling his or her thumbs. Okay, that is what is happening, and that's why upgrading the processor is not going to help. Increasing the capacity of the hard drive is also not going to help, because all that is doing is increasing the microfiche capacity of the district. How is that going to help my problem, right? The only thing that can help in this case is to basically give more pieces of paper to the student. Instead of having only 2 sheets of paper for each student, if you upgrade it to like 8 pages, that can make a gigantic difference in terms of how much microfiching needs to happen. So that is the whole subsection about paging. Do we have any questions about paging? No questions? Does anyone want a 5-minute break?
Yes, please.
Okay, so we'll have a 5-minute break and be back at 6:45, and I think that's exactly the same time as Monday, which is freakishly coincidental. All right, so we'll get back at 6:45, and then we'll start to talk about swapping.
Okay, sounds good.
All right. All right, so I hope everybody is back. It is 6:45.
I'm here.
All right, thank you. All right, so we're gonna continue to talk about swapping. So paging is only switching in and out one page at a time. So we are talking about one frame in physical memory that is saved to a slot on an auxiliary device, and then another slot on the auxiliary device can now be loaded to use exactly the same frame of memory in physical memory. So that stuff is happening pretty much transparently as far as an end user job is concerned. So there's nothing an end user job can do to basically say, oh, let's switch out a page now, let's switch in another page now. Nope, that's all done transparently. So the problem with paging potentially is we can indeed sometimes if you have very little RAM and you want to run a lot of jobs and concurrently, those jobs, even though we can run those jobs by switching in and out a lot, you can lead to thrashing. And once your system is thrashing, you're basically the productivity goes all the way down, and you are not making very good use of the resources in those situations. So swapping is an interesting concept because it is a counterintuitive solution to solve the problem of thrashing. Now, it's not only for solving the problem of thrashing, but one of the things it can do is to remove or alleviate the problem of thrashing. So the problem of thrashing has to do with multiple jobs are running at the same time, and because of that, they can be competing for physical memory frames, and that's the reason why we have to write physical frames out to I/O slots and then read another I/O slot back into physical memory frame for another address space, and then when we switch address spaces, depending on which one is running, we need to keep switching things like that. So that's the problem. So if an operating system like COS can determine that a job that is currently running but it's not really relied on by other jobs, now we can use swapping. We can swap out the entire job. So swapping out an entire job means we are writing the entire used portion of the address space of a job into auxiliary storage. And then the operating system is going to mark the job as suspended, so that the operating system does not accidentally go like, okay, let's run this job, continue to run the job. Nope, this job is now suspended. These are the reasons, and we're not going to touch it for a while. So this approach may sound worse than paging, because we are no longer writing only 4096 bytes from memory to the input-output device. We are now writing, potentially, maybe even a gigabyte. If it's a pretty big job, we can potentially be writing an entire gigabyte of content from physical memory to the I/O device. So it sounds kind of bad, right? but it's not. Now, the reason why it is actually better is because once we okay, so the first thing is your paging relies on random access to an input-output device because we are only overwriting 4096 byte at a time when we are paging. Swapping, on the other hand, is basically generating a high volume input-output contiguous operation. In other words, we are pointing to a big region in memory. Now, this is virtual, but it still boils down to a contiguous area, especially when from the perspective of the input-output device. And every time you have a high volume input-output device operation that goes to a contiguous area on the DASD, it is very efficient. Okay, because the delay is not going to be 0.1 millisecond per 4 kilobyte. It's going to be a whole lot better than that. And that's also partially because when we are talking about input-output devices at an enterprise level, they are very optimized for high volume traffic, especially when you want to write to contiguous areas. Even a DASD, even a hard drive, okay, even a hard drive and not a solid state disk, if you just say, I want to fill up all the tracks of this entire cylinder, that is actually a pretty efficient operation. Okay, even though you're transferring a lot of data, you are actually making better use of your input-output capacity in that case. So that's one reason why swapping is not quite as painful and as resource hungry as paging. But the other part is once you swap out a job, the space that was used by that job is now available, because you're not just switching out a page, you're now saying this job is now suspended. So all of the physical memory resources that was previously utilized by this particular job that just got swapped out, those resources are now available for all the other jobs that are still running. So if the operating system is smart enough and go like, okay, we have overcommitted virtual memory to physical space, it would then be able to look at the size of each job and determine, okay, if I swap out, okay, I'm just, this is just an example, okay? So let's just say that we have 240 jobs running and we are so overcommitting the resources of physical memory that we are now dealing with thrashing. The operating system would go out of the 240. If we swap out, let's say, 40 of these, then we'll have enough RAM to fit the rest. So after you swap out 40 jobs, the other 200 jobs will now run with much faster speed because they don't need to page in and page out all day long anymore, because now we actually have enough RAM to make everybody happy. So in the school setting, we're basically saying if we have only a few pages of actual physical paper, then we're going to say, we'll break the class into two cohorts. The first cohort with 16 students, the second cohort with another 16 students, and we'll go like, okay, the first 16 students, the first cohort, why don't you guys go to the playground and take a break? And then the remaining 16 students will now have twice the amount of actual physical pages, so that we don't need to we don't need to page in and page out as frequently. Is that making any sense?
Yes.
So in this analogy, we actually ended up teaching classes faster, because the amount of time that it takes to teach a class originally had nothing to do with how fast the students can learn. It had to do with how fast the district can send us the microfiche, and how fast we can back up a page on a piece of paper onto microfiche, and then send it back to the district. That was the bottleneck. But once we switch out one half of the class, then the amount of traffic, the amount of microfiche traffic can be a whole lot lower. And in the end, we can actually end up saving time, even though it is counterintuitive, because now we are breaking up the class into two cohorts. Basically, we have to teach the class twice. But when we teach the class each time, the amount of time it takes to teach the class is dramatically reduced compared to having to teach all 32 students at the same time, because most of the time, guess what? You're not teaching, the students are not learning, they're not doing a single thing, because everybody is waiting for the district to send over the microfiche. Okay, so that is the reason why swapping out an entire job and swapping out enough jobs so that there's enough resources left is actually a counterintuitive way to solve the problem. Now, there's a potential issue here, because swapping cannot be applied universally. So swapping can only be applied to batch jobs. If you have any, and also when you have interdependency, then we have a problem, because when you have interdependency between the jobs, you cannot swap one of them out, because they all need to run at the same time when there is an interdependency. So before the operating system can choose which one to swap out, it actually has to analyze and find out whether there are interdependencies between the jobs. So the job card, JCL, in a job card, when they name the DD devices, that is actually used by JES2 to understand, do we have any interdependency between the jobs? So if it knows that there is an interdependency between the jobs, then it knows whether it is okay to swap out or not, or which one to swap out. There are also other things that cannot use swapping, because if you have anything that is interactive, like web spheres, DB2, kicks, those are all the subcomponents or the subsystems that cannot be swapped out, because they are interactive. So in theory, you can swap them out, but because they're needed all the time, so that means as soon as they're swapped out, you need them back. So that's actually just going to make the system performance worse if you were to swap them out. So anything that is interactive, you don't want to swap them out. And anything that has interdependency, you don't want to swap just one out. So let's just say that you have three tasks and they have interdependency. A depends on B, B depends on A, and then B depends on C also. So they have some kind of interdependency. Well, in that scenario, you cannot swap out just one of them, but it is okay to swap all three out at the same time. Because if you are to swap all three out at the same time, then it's not a problem, okay? Because you just have to swap all three back at the same time for all three to continue to execute. So there are certain restrictions that apply when we are swapping, and those restrictions usually do not apply when we are paging. So the last paragraph, which is the last paragraph of this entire module, talks about how swapping does not actually rely on virtual memory implementation. So swapping is not paging. Now paging is something that is specific to virtual memory implementation, and so is memory mapping. Memory mapping is a required feature to have virtual memory. Paging is a convenience kind of thing, when we have memory mapping to begin with. Swapping is kind of like something that existed a long time ago. It is more or less independent to whether we are using virtual memory or not. So the example that I used here is from PC-DOS back in those days, like mid-80s or so. So with PC-DOS, they already had the concept of what we called overlays back in those days. So this overlay concept allow program code that is larger than available RAM still be able to run. Now back in those days, if I remember correctly, 640 kilobytes of RAM was the largest amount of RAM you can install on an IBM PC. And then later models can install up to 1 megabyte. But of the 1 megabyte, some region is kind of special. It can only be, it's not really quote unquote part of the program, and it's extra. Okay. But even back in those days, the concept of overlay is around, where you can, I'm not sure whether you guys remember that or not, but you can use WordStar, you can use Lotus 123, and occasionally the system would be accessing the floppy drive or the hard drive, because what it's doing is it's invalidating one overlay, and it is loading another overlay into memory. So this way, it is not quite the same as swapping, because there's no swapping out. It is only swapping in, or it's only reading in, but it makes it possible to make a program that otherwise would not fit into RAM to basically run, because now you can break up the total amount of code space into portions where you say, okay, this bunch is needed at the same time, so we'll put all of those into the same overlay. This bunch also belong together, they'll be in another overlay. I can give you an example. If you're using WordStar, which is a word processor, all the subroutines related to interactive typing, they all kind of belong together. Okay, so that would make one overlay. But when it's time to print the document, and the user is not going to be interacting by typing, editing the document anymore, then all of the logic that has to do with translating the content of the document to some form that you can send out to the printer, that belong together in a different overlay. So the key idea is, when we're using that concept, we don't want overlays to depend on each other, because there's no way to load multiple overlays at the same time. We can only have one single overlay at a time. So we want to make sure that everything that is interrelated stay within the same overlay. So that's back in the old days when we had PC DOS, and I think 640 kilobytes was the upper limit of how much RAM you can install on those computers. So that's just historical reference, to basically, let you know that swapping can be done without virtual memory. Do we have any questions about jobs? Module 340.
I have a question.
Yeah, go ahead.
This is Jennifer.
Yeah, go ahead, Jennifer.
I know we're talking about jobs. So are these all, like when you write the JCL for this? Are these like, if you want to do, we're talking about mapping. So do you write that in the JCL or no?
You don't write it into the JCL, because as far as the job is concerned, it can only see things from the perspective of the virtual/logical address space. So as far as the job is concerned, it is just happily reading from one page to the next, moving on to the next page, moving on to the next page. Now occasionally, okay, think about the student perspective, right? So the students are the jobs. The student looking at a binder, the history textbook in this case, is totally, the student is 100% unaware that the student only, okay, first of all, 384 of those pages are actually shared by the portal technology. The student doesn't know that at all. Okay, the student would actually look at the textbook and go like, nope, this looks like a regular textbook to me. I don't understand why you guys are talking about portals. Okay, because that is completely transparent from the perspective of the jobs. Then what about those special pages, like each student only has like 4 or 8 physical pages corresponding to the exercises? Even that is entirely transparent to the student. Now you might say, but how can that be possibly transparent to the student? Because when the student flips from the last actual physical page that has an exercise onto the next page, which actually does not exist, but it should have corresponded to the next page of the exercise, how can the student not know about it, right? That would be a natural question to ask. So the paging technology requires two components. One component is a hardware thing, it's coming from the central processor, and then the second component is coming from the operating system itself. So ZOS has a component that handles the memory mapping. It basically has a translation table which goes like, okay, which page in virtual space is where? Okay, is it in memory? If it is, where is it in memory? If it is not in memory, it has to be on an I/O slot. If it is on an I/O slot, where is that I/O slot? So it has a translation table to do all of this. So getting back to this, yeah, go ahead.
I'm sorry to cut you off. The software mechanism is the one doing this, right?
Right. So, but the job itself is completely unaware of all of these things happening in the background. Okay. So, I'm not sure how much you guys want to get into this, but when the student flips that page to try to read a page that it does not exist yet, at that moment, time is frozen to the student. Okay, as soon as the student tries to flip that page, time is frozen, because this is a hardware thing. The hardware knows that a task is trying to access a page that does not exist. It's called a page fault, by the way. So when the page fault happens, it happens in the form of an interrupt. Remember how interrupts are asynchronous to the jobs? A job doesn't know that the interrupts are happening. This is one of those things, right? So the job doesn't know that there's an interrupt that just happened. So the interrupt is now going to into the ISR, the interrupt surface routine, which contains the logic of looking into this interrupt, go like, okay, let's see what just happened. So that is a part of the operating system. The ISRs are a part of the operating system. So the operating system look at the reason for the page fault, and then the first thing the operating system is going to ask is, well, is that page even legitimate? Okay, is the student supposed to have access to that page? And if the answer is yes, then the operating system will go like, okay, well, if it is not here, if it's not a physical frame, in other words, if a virtual page is not corresponding to a physical frame, and the processor is about to execute on that particular page, then the operating system will go like, okay, let me find you a physical frame so that I can map that virtual page onto that physical frame. In other words, the operating system, in this case the school, is going to say, okay, let's just scramble and find an actual piece of paper, and we'll get the right content onto that piece of paper before the student resumes to read the following page. And all of that stuff is happening in the background. The student does not know all of these things that's happening in the background.
Okay.
All right? Okay, cool. Yeah, this is something that I learned in assembly language programming, when I was studying at San Francisco State University. And I think the year was 1986.
So,
yeah.
Is it the coupling facility that does all this, that takes care of it all, or?
Actually, no. All of this stuff here is so. It depends on the CF may be involved, but most likely it is not the case. So most likely it is really just the CP in the CPC drawer that's executing the page, that's executing code on the pages, and when it tries to continue to execute on a page that does not exist, that is not corresponding to a physical frame, then the operating system kicks in, and it would load the I/O slot corresponding to that page onto a physical frame, and then it will update the translation table of where things are. So by the time execution resumes onto the task, then the translation table would have the proper entry to say that this page in virtual space is corresponding to that frame in physical memory, and then the processor would then be able to continue its execution. So the CF is most likely not involved in this process. The CF is involved when we have two tasks. One task is running on a particular IBM system, which is one single mainframe, and then another task is running on a different mainframe, but the two mainframes are in the same sysplex. So when that is happening, and one is changing the shared memory portion for communication purposes, then the CF is involved in this case, because the CF is the conduit between the two mainframes. So the CF is going to update the other mainframe computer, so that when the task on the other mainframe computer tries to access the so-called shared memory region, it will see the same content.
So like at my work, we have like in a sysplex, we have like LPAR, it's called Sci7 and Sci5, and they mirror one another. So that coupling facility, like if a change is made on Sci7, the coupling facility then goes and changes it on Sci5 as well to mirror it.
Yep.
Okay, got it.
Yep. Yeah, if you think about it, it's truly marvelous. Okay, that this can be done in a way that is transparent, because you basically have two physically separated mainframe computer, but everything is synchronized, lockstep, to the point where one can go down and then the other one can take over like right away.
Right.
Yep.
Okay.
Yep. This is why IBM is paid the big bucks. All right. So we are now done with all about jobs. I do have content ready for IPL. I was working on that, I think yesterday or earlier today. I cannot remember. So we'll go take a look.
I went and tried to see if we had the option to show the like table of contents for your module, and we don't.
Oh, okay.
And we don't have any options that are available. You said it was in add-ons, right?
Yeah, it's an add-on, but I think the add-on is available only to the editor of the document.
Yeah, because I went and tried, and it wasn't available.
Darn it. That would be helpful. So what I can do is I can do this. So the IPL, I can do the same thing with other modules too, but since some of you might have printed and this is going to change the page number, I'm not going to do it unless you guys say, okay, we are good, and let's go ahead and add the table of contents. So this is the table of contents, which I think from your perspective, you can click and go to the section like, just by clicking it.
If you could do it on the prior module, because I know people have already printed it, but if they, choose to go back and reprint it, because that had a lot of information in it, and I thought that would be useful.
Okay. All right.
Thanks.
Yeah, just let me know when is a good time to add the table of contents, because I want to kind of let people, get ready for that. All right, so we're going to talk about IPL, for maybe another, 20 minutes or so, because then we're going to be running out of time today. And I think this is going to be about, just looking at the scroll bar. I think this is going to take more than 22 minutes, so we're good. We got enough content. All right, so IPL stands for. It just blanked out in my head. It's initial program load, right? I'm gonna look it up. Sorry about that. So IPL does stand for initial program load. Okay, let me just kind of add it here.
Okay. Will 341 be ready for us to print next class?
Next Monday, yes.
Okay, thank you.
So I will be working on this for a little bit more. This one is almost done, but I still want to add a little bit more to it. So it will be ready in maybe a few days. I'll send a note when I think it's ready to go. All right. And remember, next week is supposed to be taken over by the next professor. And that one is still kind of up in the air. I really do not like it, when things are up in the air like that. So anyway, we're gonna keep going. Alright, so IPL is the bootstrapping, more or less, of an IBM mainframe. So what I have not included in the document yet is there are different types of IPL. There's cold boot, there is warm boot, and there's one more that I cannot remember the name. So cold boot is easy, okay? You just, you're powering up the system, okay? You previously the system was not even plugged in, and you plug it in and then you turn it on. That is a cold boot. A warm boot, there are two types of warm boots or lukewarm boots, however you want to call that. It depends on how much of the system can remain as it is, and then which portion is reinitialized. So there are two levels of reinitializing the system without starting all the way from scratch. So that is one portion that I have not written yet, but I have been reading those documentations. So we'll get to that next week for sure. But what we're going to do today is to start with these major steps. So the first major step is a person, the system administrator, the system operator, or the system programmer, which I thought was kind of interesting because most programmers typically do not operate the mainframes. But in all the IBM documentations, they refer to system programmers, that can initiate this operation. So the HMC, the Hardware Management Console, is a user interface, and it's a user interface corresponding to the Type 1 hypervisor, which is PRSM. So that is basically just corresponding to the configuration of the virtual machines. So from that interface, you can initiate a cold boot, from and start the IPL. And the parameters that the person can specify would include the IPL volume. So the IPL volume is corresponding to a DAS-D. So of all of the DAS-Ds connected to a particular mainframe, even though it's virtual, it's a LPAR, but you can still see all the possibly virtual, possibly non-virtual volumes connected to this particular installation, but you can only have one to be used for IPL. So you have to identify which one is used for IPL. You can potentially have multiple volumes that can be used for IPL, but for every single boot, you can only say, this time we want to start with this one, or this time we want to start with that one. Okay, so you still have to designate the volume that you're going to use for this particular bootstrap. The IPL volume would contain bootstrap code. Unlike other volumes, an IPL volume contains bootstrap code on track 0 of cylinder 0 of that particular DAS-D. Now, even if you're using solid-state device, solid-state drive, logically, IBM would still be using track and cylinder to refer to portions, basically, blocks of data on that device. So there's still a logical track and a logical cylinder in that case. Now, this particular volume is also known as the CISC331 volume. I'm not really sure, what CISC331 is.
System resources.
System resources. Okay.
I believe so.
Okay. So it's also called the CISC331, volume. The operator will also specify the IODF, which stands for Input-Output Definition File. And because it's a file, it has its own volume and its name, as a data set. We'll talk about this later. There's a in the later step, there's more detail that talks about where to find the IODF. So basically, it defines one IODF can contain the parameters of multiple configurations. So you can basically store configurations in the same IODF, and then in that case you have to use a load, and then XX is representing a number. So that would basically identify the exact configuration that you want to use for this particular IPL instance. So you can basically store multiple things and go like, if I want to restart the system using the older version of iOS, I'm going to use this configuration. But if I want to start it with the latest and greatest version of ZOS, we'll use that particular configuration. I said iOS earlier, I meant ZOS. So it gives you the flexibility of choosing which system you want to start. Okay, you can have revision control. You can say, okay, the new version may not be compatible. We want to try the same thing again using an older version. So this gives you the flexibility to do that. Oh, okay. System residence volume. Thank you, Carrie.
It was Loopy.
Oh, it was Lupe?
Well, he's the one who told me.
Oh, okay. Well, thank you, Lupe. All right, so I'm going to copy and paste it. There we go. Oh, let me do that. And get rid of the pro. There we go. So the system parameter includes operating system data, switch data. When they talk about switch, it's in the context of a network switch. Device data, processor data, so that would be your CP. Partition data, I think partition refers to LPAR type of partition. Because there are only so many terms people can use, so when we look at the word partition in the context of a PC, that refers to a portion on a hard drive, which logically is one thing. But in the context of IBM documentation, I believe this partition refers to LPAR type of partition, logical partition. Channel has to do with input-output. So channel path is how do we get to a particular channel, and I have no idea what these other two are referring to. But basically, each configuration identified as load and with 2 digits is giving you some parameters that will be used later on during the IPL process. So the next step, okay, so this first step is a user-initiated operation. An operator, goes to the hardware management console and specify a few items, and then start the process. So the next one corresponds to the first stage of the bootstrapping process, or basically the first step of the IPL. Now I break up the process into first, second, and third stage. Those are not IBM terminologies. So if you ask anyone who knows IBM stuff and say, okay, what about the second stage bootstrap, they would have absolutely no idea. But in my head, I had to break I have to break the long process down into main steps, and this is basically just me breaking up a complex process into multiple smaller steps. So I just want to make it clear because these are not IBM terms. So the first stage is performed by I put the word probably here because I really do not know. I try to find references that talks about this, and I could not find it because these are really low-level stuff, and there's no reason why IBM has to release documentation about this particular component. But knowing computers in general, this step is usually done by a system firmware in combination with the HMC specified parameter to the Type 1 hypervisor. Now remember, Type 1 hypervisor itself is firmware. In other words, it doesn't need to be loaded, it doesn't need to be bootstrapped, it is always there. So that's what a type 1 hypervisor is in the context of an IBM mainframe. So what that does, the bootstrap module is first going to be loaded. It's going to be copied from track 0 and cylinder 0 of the volume identified as the IPL volume in the earlier step, and that the content of that track is going to be loaded into memory location 0. Now when I say it's copied to physical memory location 0, it simply means starting with location 0, because location 0 is one single byte. Okay, you cannot have usable code using only one single byte. So this only means that we are starting with memory location 0, and then whatever the size of a track is going to be loaded starting at location 0. And we are talking about physical memory here. Okay, this is not virtual, this is not logical, this is physical memory. And then execution would start at location 0, which is basically the location that just got content from the IPL volume. And then the bootstrap code would read the IPL text, which is also known as IEA IPL 00, also known as the IPL control program. So right now, okay, so right at this point, the question is, but why don't we just read the IPL text to as the first step? Why do we need to read track 0 of cylinder 0 first, and then have that code to in return read IPL text into RAM to execute? So, I mean, if I were you, I would ask that question, and probably you're asking that question too. It's like, how can we have it's like a rocket, right? You have first stage booster and then second stage booster and so on. So the answer is, I think the earlier mainframe computers are simpler, and they can only handle reading a single track into physical memory in order to start the whole process. So the current generation of hypervisor, which is a firmware, obviously it's a lot of code, can be very complex, but that was not how things used to be. So in order for things to be backward compatible, they're maintaining the same method. So the first stage is basically something that probably can be done with very old mainframe computers as well. So basically the first stage is just the first step of the first stage, reading from track 0 of cylinder 0 to location 0 of physical RAM and start running that code. That is just backward compatibility. So this code that is in IEA IPL 00, which is also called the IPL control program, is there's no references whatsoever. I could not find any information of where it is on the volume. I just know, okay, everything that I have read just says that this is on the IPL volume. But when you look at the picture, they seem to imply that this is actually just following track 0 on cylinder 0. Okay, but that part is just me extrapolating from existing information, so I'm not really 100% sure about the location on the volume of where you can find IEA IPL 00, but I just know that it has to be on the same volume. We talked about this already. It's for backward compatibility. So the code contained on track 0 of cylinder 0 is probably a whole lot smaller and simpler and shorter compared to the code contained in the IPL control program. The IPL control program is going to be longer, and this is basically, now we're talking about the second stage of the bootstrap process, is running the IEA IPL 00 code. Are we still doing okay so far with the explanation? Okay.
Yes.
All right, cool. Now, this is actually the other interesting thing about the bootstrap process that I have talked about so far is your PC actually has a very similar bootstrap process. It goes to sector 0 of track 0 of to read. I think in the case of a PC, I think one sector is 512 bytes. So it will read that 512 bytes into the lowest region of RAM, on your computer, and then it will run it first. And then that code in return will load a larger chunk of code to run. So it's actually interesting because there's a certain mirror between how a mainframe computer starts up compared to how a PC starts up. Now it's not really surprising because it's surprising in a way, but not so surprising in other ways, because a PC was an IBM product. If you track all the way back to who manufactured the first PC, it was IBM. So in the mid or early 80s, sorry. So in the early 80s, IBM introduced the IBM PC. The surprising part, remember I said one part of this is not surprising, and yet the other part is surprising. So the other part that is surprising is PC-DOS was actually not an IBM product. IBM PC was an IBM designed product, but then PC-DOS was not an IBM product. It was actually a small company that made a CP/M clone for other computers, and then Bill Gates bought the right to that operating system, and then that became PC-DOS. So it's kind of convoluted, but I'm not gonna spend too much time to talk about that. All right, so second stage of the bootstrap process. We'll probably finish a part of this and then wait until next Monday to finish it. So at this point, there's still no such concept as a task, no such concept as a thread or process, because there's no operating system at this point. So this is code. It is running from RAM, but there is no operating system to talk about. So without an operating system, we can't really define what is a task or a thread or a process. It's just code running, from RAM. Physical memory is accessed and cleared. So this part is actually explained in IBM documentation. So basically, physical RAM is going to be assessed, not accessed. This is assessed and cleared. This has to do with physical RAM. When we start up a computer, DRAM is uninitialized. So when you first power up a computer, the RAM content is just random stuff, random zeros and ones. So that obviously needs to be cleared. So the next question is, why do I choose to use the term assessed? That has to do with an installation initially does not even know how much RAM it has. I mean, really, it does not know how much RAM it has, because depending on what type of DDR4 DIMMs you install, the amount of memory available to a particular CPC drawer can be different. You can install smaller DIMM modules, and then you have a smaller amount of RAM. And if you install large capacity DIMMs, then you end up with more capacity. So initially, the system doesn't even know how much RAM is available, and it has to basically do some kind of scanning to find out, how much RAM is actually installed in the computer. And that is a crucial piece of information, because unless the bootstrap code knows how much RAM is installed, it doesn't know how to put things into physical memory. So that's the third item from the top. So the fourth item here says the control program has code that understands how to locate datasets on the volume, and this is how it can find sys.nucleus. So sys.nucleus has to be a dataset on the IPL volume, but it is not at a fixed location. It doesn't have to be at a fixed location, because at this point, with the IPL control program, otherwise known as IEA IPL 00, so that piece of code contains the logic so that it knows where to find data sets by name in the volume. So sys.nucleus is the name of the data set. It has to be on the IPL volume, and then at this stage sys.nucleus is located. And then the basic environment for the kernel of the ZOS, which is also called the nucleus. So the nucleus does not refer to the entire ZOS. It refers to only the most crucial part of ZOS, which in this case, consists of a few items that will be discussed later. So when you look at the term kernel, especially for those of you who are going to take a class in Unix or Linux, when they use the term kernel, it really is referring to about the same thing as the nucleus. It's the same thing as the nucleus of ZOS. It's the same kind of component. It's the innermost core of an operating system. So now we set up the environment, and we'll be reading and executing the IRIMs. Then each one is a IPL resource initialization module. So at this point, it's going to interpret load param. And what load param will do is it will specify how we can find IODF, the input-output definition file. And once we find the IODF, it would also specify, load param will also specify which configuration we're going to use within the IODF, because an IODF can contain multiple configurations for IPL, and we will need a specification of which one to use in that case. And the process involves checking the existence of these particular data sets. So it will check from sys0.ipl param, and then if that does not exist, it will move on to sys1 and then move on to sys2, and the very last one is going to check whether it exists or not. It's sys9.ipl param. If none of those exist, then it will go to sys1.paramlib to try to find the load definitions. If that is also not there, then the bootstrap process would actually be paused. I'm not sure whether it would actually display anything, because I don't think the console is connected at this point, so the system would probably just hang and not to continue the process at this point. If it does find the load configuration, then it's going to read that configuration. So the next step is to load the nucleus into physical memory. So it's going to read sys.nucleus and then put it in physical memory. The nucleus, okay, this part is also very important, because this part is actually also true in the case of Unix and Linux and also Windows NT, is the kernel or the nucleus, because those two terms refer to pretty much the same thing. That is one part of the operating system that cannot be in virtual memory. In other words, there can be no paging in and out. Okay, that portion of the operating system has to be resident in physical memory all the time. Okay, so that kind of helps to define which part is nucleus and which part is not nucleus. And then I'm just going to finish the rest of the bullet points, and then we'll leave 1.4 for next Monday. So the next step is to initialize virtual memory storage. There are different types of SQL within the address space. So if you go back and look up the address space map that we talked about on Monday, you would notice, okay, there are 3 SQA regions. One is the regular; it doesn't have anything before it. The other one is extended, and then one is local. So all of those are initialized in this particular step. And this is interesting because this area is shared by multiple address spaces corresponding to jobs and tasks. And then the next item is to initialize memory management memory management data structures. Remember we talked about the page frame table? Basically it's a map, so that the operating system can say, oh, page blah 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 of this virtual address space corresponds to this particular frame in physical memory. So there's a table to do the mapping. Segment tables, I looked it up. The links are in footnotes 4 and 5. They correspond to regions in memory that can be shared by a group of tasks. So basically it is still a data structure that has to do with how different tasks can communicate with each other by sharing memory. So remember that analogy that we did earlier, how two different students in their textbook, they can map to the same page, so when one person doodles on that page, the other person gets to see that doodle right away. And the next step is to replace the area starting at location 0. So that area was originally, so the first thing we loaded into that location was track 0 of cylinder 0 of the IPL device. And then after that, we also loaded the IPL control program right after the content of track 0 of cylinder 0. So all of that stuff is now replaced. Okay, it's going to be replaced by the PSA, which is the prefixed. Oh, okay, typo over there. It's the prefixed save area. Now PSA, if you remember from Monday, PSA is specific to each CP in the CPC drawer. So this area is kind of interesting because it is specific to each processor. And then the last IRIM, which is the IPL resource. I have to look it up because I cannot remember the acronyms. Where is that? Oh, right here. So IRIM stands for the IPL Resource Initialization Module. That's it. So the last of those modules would load the first part of the NAP, which is the Nucleus Initialization Program, into RAM. Whew. Okay. So we're going to stop here. I'm going to put a little bookmark here. Okay, so we'll say last topic on
Twee
the
has her
28th.
hand raised.
Sorry?
Twee has her hand raised. Maybe that's old. I don't know.
Oh, sorry about that. Go ahead.
Is it low param or low palm?
You mean this one?
Yeah.
I think it's without the second A. You're correct. Do I have any reference to it earlier? Yeah, I think it doesn't have the second A. Let me look up right away. You're right. It doesn't have the second A. All right. So there we go. Thank you. All right. So that's the end of today's lecture. So next Monday, we are gonna start with section 1.4, and as I said earlier, I'm gonna keep typing. There's a little bit more to type to finish up the IPL. One thing you guys can do, if you have the time, is you can check with your manager or your mentor, and I just want to know, generally speaking, what they are expecting you to learn from the RSI. The curriculum right now is determined by IBM, which is not specific to your job. It's not specific to the state agency either. We don't have to go. We don't have to follow the IBM curriculum, all the way. So, one thing that both Mark, who's another professor teaching IBM mainframe stuff, he's mostly on the COBOL programming part aside. So one thing that we want to do collectively is to find out, how can we, being the instructors of the RSI classes, communicate better with the manager and the mentors so that we can teach the content that is relevant to what you are going to do when you're done with the apprenticeship program, instead of just going through the stuff that IBM thought would be useful. So that's one thing that you can kind of bring up with your mentor or your manager, when you have the time and when it's convenient. It's not a requirement. I just want to know a little bit better of the context of these RSI classes.
Would it be helpful to you if I sent you my duty statement for the position that I'm training for?
That would be really helpful. Yes.
Okay.
Yeah, that would be very helpful. Hopefully, the duty statement would actually include technical terms referring to the specific things that you're going to do.
Yeah, I think it does pretty well.
Yeah, that would be very helpful, because sometimes duty statements can be very vague as well.
Okay, I will send it through the Canvas email to you tomorrow.
Yeah, that'll work. Thank you.
Okay.
What is RSI?
OSI? RSI. So RSI stands for something supplemental instruction. I cannot remember what the R stands for. Okay, let me look it up. I can find that. RSI. Alright, so I know what RS stands for. It's supplemental, and then I is instruction. I just cannot remember what the R stands for. Oh, okay, it doesn't have it. I'll find it and tell you what it is. But basically, RSI is it refers to the content of all the classes that you're taking through ARC, and it is supposed to supplement what you're learning with hands-on experience with a mentor and your manager at work. So that's what RSI is referring to, is the content of the classes that you're taking. And I would like it to be actually relevant to what you need to know, but I can't do that easily without having communication with your manager or your mentor. The people who determined the RSI, one part of this had to do with IBM. So IBM basically pushed the same RSI to all of its clients. Okay, so it's not specific to the state, not specific to any agency whatsoever. This is like just a boilerplate from IBM's perspective, and go like, this works for all of our clients, it should work for you. So that's one. The second one would be the people on the JAC, the Joint Apprenticeship Committee. So those people, the representatives or the reps, from various agencies, from what I was informed, from what I was told, those people tend to be higher up in terms of the organization chart, from the org chart, and they may not know, at the ground level, what people actually need to know. So I think there may be a disconnect between what we think we should include in the RSI as opposed to what you guys actually need to be included in the RSI. So I just want to kind of make sure that I'm not wasting your time, learning something that ends up basically being pointless, when it comes to your job.
One thing that I've always been saying all along that would be most beneficial is to learn how to read the IBM manuals, because they're so technically written in diagrams that I have no understandings of what they're trying to tell me when I'm looking up trying to do something. Like coding something in Rex or whatever. Their diagrams are so bizarre that an explanation on how to read those manuals would be invaluable.
Okay, so I have some answers to that question, like right away. I can do some more research and give you a longer and more elaborate answer. But I got like two aspects of, I can address two different aspects to what you're asking. The first one is, even if you have a bachelor's degree in computer science, you will still feel about the same. I hate to put it that way. You'll still feel about the same even if you graduate from UC Berkeley with a computer science degree. You will still have that same feeling because IBM uses terminologies that are different from the mainstream terminologies. And IBM programming languages are also not mainstream. In other words, if you just go out to UC Berkeley, okay, grab a student in computer science and ask that student and go like, do you know what is JavaScript? Oh yeah, totally. Do you know the Intel i7 architecture? Oh yeah, we studied that too. Do you know about blah blah blah? And if you are asking about mainstream stuff, they would know something about it. And then when you say, do you know how to program in Rex? No. Do you know what is COBOL? No. Do you know what is JCL? No. That is the kind of answer that you're going to get, okay, from almost any student at a university. You go to the Silicon Valley, you grab a software developer, you ask the same questions. Guess what? You're going to get the same answers. So it is difficult because there are very little secondary resources that you can find when it comes to IBM specific technology. If you want to learn JavaScript, okay, and you go to Amazon and you look up JavaScript books, tons, okay, the difficulty is finding which one is going to work for you. But if you go look for documentation on Rex or JCL and stuff like that, eventually, there are few out there, okay, but not a whole lot. So you're not going to be able to select, which tutorial or what resource you can use. So that's one problem. The second problem that I can see, because I have to do all the research to prepare for this material, is IBM documentations are very they're more like documentation so that the technical people can remember, how the system is designed, but they were almost never really written in a way for people who did not know anything about IBM systems to start understanding the system. They don't have the introductory material to get the concepts in, so that you guys can gradually build up your knowledge of the system, so that you can go like, okay, this is the first level of knowledge, and then we build on top of that layer, and then we build on top of that layer. I think that part is kind of lacking. So I think those are the two issues that I can, identify like right away.
I was just talking about like looking in the Rex manual and trying to find, a specific topic on how to code something, and just being able to interpret their diagrams or their flows that their manuals have within them is just, it's like so confusing that I can't get anything out of them because I don't understand their logic behind their manuals.
A lot of the stuff that IBM does, has to do with backward compatibility. So from the perspective of someone who just starts right now, who has no knowledge of the background of all of this stuff here, things would be odd and strange and go like, why do we do it this way? I think somebody brought up, the above the bar and below the bar thing from Monday.
That was me.
That was you, exactly.
Yeah.
So that doesn't make sense, right? I mean, it doesn't make sense unless you understand, oh, so IBM have been making mainframes since the 60s, okay? And the mainframe in the 60s only has this much memory, and then they bump it up to this much, and then they bump it up to this much, and because of that historical record, because of that historical thing, that's so what we are looking at, when we looked at the address space, all the boundaries,
Right.
it's basically it's almost like the DNA of the
Right.
system that traces all the way back and go like, yeah, we kind of started as bacteria.
Right. I get that.
But when they don't explain that, and they just give you the picture, it's like, okay, we got SQL here, we got local SQL over here, and then we got extended SQL over here. You go like, Why? Right? Because normally it doesn't make sense. Why don't we just have one single SQA area? SQA itself makes sense. Okay, it is for you for a task to communicate with the operating system in a very efficient way. Okay, I get that, but why do we have three different SQA areas within the same address space? So until people understand, oh, okay, so this is for backward compatibility, okay, so that old programs compiled by old COBOL compilers running on an old version of an operating of MVS, okay, can still run, using the latest and greatest, mainframe hardware that we have today. But until people have that knowledge about the intention of these things, they won't understand. They won't be able to connect, all of these things. So I feel your pain because as I go through all of this material, I have to go through the same thing. I cannot just look at something and go like, okay, this is what the document says, and I'm just gonna repeat this to my class. I can't do that. I'm sorry.
I feel ya.
I'm ranting right now. So um, of all the things, I mean, this is also the strength of IBM. Is they really um, maintain 100% backward compatibility. I mean, there's no other company that would do that. Um, but that's also because a lot of the older programs, they're only modified in a minimal way to keep up with whatever tax code or whatever uh, law changes since
Right.
the olden times. So because all those changes are so minimum and people don't want to take the risk and go like, I mean, I know we are running out of time, but I do want to kind of bring this up because sooner or later you're going to be exposed to these things. So there are people who go ask, okay, why don't we just rewrite all the COBOL programs from the 60s and rewrite all of those programs in JavaScript, in Java, whatever programming language, modern ones that you want to pick. Okay, it doesn't matter which one. We're gonna rewrite all those programs, so now we can run it on a modern, architecture, using Google Cloud and blah blah blah. Well, because that's a huge risk. Okay, if the franchise tax board made a mistake, it's gonna cost a lot. Okay, to the state, to all the stakeholders and whatnot. If the DMV makes a mistake, it's going to be very costly. So because every step along the way, we don't want to do something that is costly, we ended up, um, with a with a with a huge collection of these programs, that are written in COBOL. They're maintained, they reflect changes of the law, but for the most part, they're still using logic and COBOL programming style from the 60s, maybe the 70s, maybe the 80s, but they are not modernized. Um, so this is both the strength and also the strange part of working with IBM mainframes. I'm done ranting.
Okay. Me too.
All right. Well, I know you guys are tired because you got a whole day of work, and then you have me, talking, yakking about these things. So I'm gonna let you guys go and have a nice weekend. And if you can review the material, that might be helpful because if you identify something, you go like, I'm not quite getting what that means. You can always just kind of leave your comment, and I'll go back and try my best to explain those.
Thank you.
Okay, thank you, Jack.
All
Have
right.
a good weekend.
You too.
Bye.
Okay.
Bye.
Bye bye.
Weekend. Bye.